Okay, Year 12. Today, what we need to do is we need to get a move on to the course. We're going to look at compound areas, and what I want you to think about when you hear that word compound areas, it's kind of like what we talked about all the way back in Year 7, Year 8, Year 9 and 10 with composite areas. We're looking for things where we can add shapes together like we did before, take shapes away, um, identify what's happening. And where we're going with this one in particular now is what is happening when we are looking not just between one curve and the x-axis, but multiple curves and different points of intersection. So to help us with that, one thing we want to look for is we want to look for symmetry. Mathematicians, we're efficient. Let's try and find the simplest way of doing things. So when we're looking for symmetry, we're looking for our odd and even functions and what we know about those odd and even functions, and tie everything in with odd and even functions and everything we know about curve sketching that we've done so far. Once we've looked for symmetry, if it's there, brilliant. If it's not, okay. What else do we need to be wary of? We need to be on the lookout for crossover points. Where are our graphs intersecting? Is it going to be a case like with composite areas? I'm putting two different parts together, and am I taking parts away from each other? And something we're going to get into when we're looking for these crossover points is one curve always under another curve over that interval that we've been asked to find the area? Because if it is, we've got a hard and fast way that will always work when one curve isn't always entirely above another curve. Right? So let's get into this. Here is we want to find the area of that green shaded region. Another way of describing that region is the area bound between the two curves and the x-axis between x equals 2 and x equals 6. Right? So if we're having a look at this, looking at those ideas we talked about earlier, here is a crossover point. So if I think about this one, I can kind of divide here, into two sections. I'm going to get this area here, and then I'm going to add it with this area here. So that seems okay. I'm just going to add two things together. So what we're going to end up with is the area is going to be equal to the integral evaluated between 2 and 4 of x minus 2 all squared, plus the integral between 4 and 6 of x minus 6 all squared. Remember, having a look at this, expand out, and off we go. Now, looking at that, integrating that, we've got the skills to do that, but it's a lot of hard yards there. Mathematicians, we're lazy, efficient, however you want to look at it. Can I get it around not doing this? And the answer here is a sneaky yes. If we come back up and look at both curves are just as sneaky y equals x squared, but they've both had a horizontal translation applied to them. We've shifted them all to the right. Like g of x has been shifted right 2 units, and f of x has been shifted right 6 units. So that's interesting. I can drag everything back. I'm going to think I want to drag everything back to the origin. I can manipulate both curves, changing that and getting them all back so the vertex sits at the origin, quite simply by just shifting everything left. When I'm shifting everything left, what I'm going to end up with is, with this curve here, I'm going to paste that here. If I'm shifting everything left, like I said, I've got to take 2 units away from my upper boundary, and I've got to take 2 units away from my lower boundary. So I'm now just integrating, when I move everything back to the origin, between 2 and 0 of x squared dx, which is great. Now I'm looking at the blue curve, and I've got to take the blue curve as well back to the origin because I can. And again, if I'm shifting it back to the origin, I'll do it in blue, everything is going back 6 units. So I'm going between 0 and -2 of, alright, so then it's just going to be between 0 and -2 of x squared dx. So that's awesome. I can look at that, and what does that look like visually? Well, when I move everything back to the origin, what I've got is this area here and the g of x curve, which is this area here. Oh, we're just finding those two parts. This is where now symmetry comes into it. And what we're going to end up finding here is the area that we had between these two curves. If we took the time and looked at, okay, everything's been just shifted right a couple of units, I can bring the vertex back to the y-axis. And when I do that, I'm just left with this, which is really, using symmetry now, the area is equal to 2 lots of the integral between 0 and 2 of x squared dx. Right, using that symmetry. So just quickly going on and solving that, that is going to be 2 lots of, add 1 to the power, x cubed on 3, evaluated between 0 and 2, which is just going to become 2 lots of 2 cubed on 3. Let's just do it properly. That minus 0 cubed on 3, which is just then 16 on 3 units squared. Now, I don't know about you, but integrating x squared by itself is going to be a lot simpler and straightforward than having to integrate and evaluate all of those terms. Doing it the long way still gets you to 16 on 3 units squared. But let's use all the skills that we've developed in this course so far. Alright, take a moment to just pause and reflect on the curves that you have been given. They are just normal parabolas shifted right. We can bring them back, and it worked really nicely with our symmetry response here. Alright, so looking at what happens between curves here, and I've got an example here. We've got 2 graphs. We've got the graph of y is equal to x minus 4, and we've got the curve of y is equal to, it passes through 1, so x minus 1, x minus 4. That's our parabola. Reading it quickly, and you can see that's going to expand to x squared minus 5x plus 4. And I'm going to tell you right now that it doesn't matter where your curves lie, the area between curves, the area is always equal to the integral of the top minus the bottom. Alright? With respect. Alright? It is always going to be that way, no matter what situation that we have. Alright, so let's have a look at why that's going to be the case with this example here. I think this example here, because it invokes us going, but it's negative, it's below, below the x-axis, what's going on here. And intuitively, we've done in the past, just take the absolute values of this and you're off and running. But we're not going to do that here. I'm going to describe this differently, right? We did that because we took the absolute values because we know that when we evaluate the integral and the section that we're evaluating is below the x-axis, we know that our result is going to be negative. And really, if we think about what we want, it's we evaluate all of this area and we then just take away that little triangle part there. That's what we're going to want to do. But that's not what I've got written down here. What I've got written down here is the straight line minus the parabola. And explaining what's going on there is that, well, we know that when we evaluate that, we're just at the moment evaluating it, we know that in that section between 2 and 4, that straight line exists below the x-axis. Because it's below the x-axis, we know that it's going to produce a negative result. Let's just call it, negative 8 for it's going to produce a negative area. It's going to produce a negative value. All right, it's not technically a negative area, but let's just call it negative 8 for the moment. And we know then that for the exact same reason, this is also going to produce a negative response. But what we have in between them is a minus sign. And we know that this negative sign next to that is going to become positive. So this actually becomes all of area 2 minus area 1, which is what intuitively, instinctively we want to do with this kind of situation. And no matter how these curves appear to us, no matter what their order, it is always going to be the top curve minus the bottom curve, no matter whether it's part above, part below, all above, or below. It is always going to be the top minus the bottom, the top minus the bottom, the top minus the bottom. It is always going to be that case. The things we need to be careful for, though, are examples like this one here, where at this point here, the top and the bottom curve switch directions. So we need to be aware of that. Okay, moving on. All right, example 2 here. The diagram below shows the curves y equals minus x squared plus 4x minus 4 and y equals x squared minus 8x plus 12, meeting at the points 2 and 0, so 2 and 0, and 4 and negative 4. Find the area of the shaded region. Okay, so finding the area of this shaded region here. One thing that let's take the time to break down what's happening. We have a point of intersection over here where the two curves cross over each other. So we need to find this area in 2 chunks. We've got area 1 and we've got area 2 down here. All right. So with area 1, what we're looking at here is we're looking at an area and it's bound between 2 curves. All right. So we know it's going to be between 0 and 2. We can read that from the graph. But what we need to ask ourselves now here is which curve is on top. Because remember, the area between curves is always the top curve minus the bottom curve. So the top curve, well, it's the positive parabola, so it is going to be x squared minus 8x plus 12. And we're going to take away from it the bottom curve, minus x squared plus 4x minus 4 dx. All right, and simplifying that expression inside before we go through and do our integration. Be careful of negative signs, that negative and that negative there. So quickly what we're going to end up doing is we're going to evaluate this between 0 and 2, x squared, so we've got 2x squared minus 8x minus 4x becomes minus 12x, 12 minus 4 becomes plus 16 dx. We're going to evaluate between this and without actually going through and doing all of that, I'm going to tell you that that becomes 13 1/3 units squared. So that's our area 1. Remember that the area between curves is always going to be the top curve minus the bottom curve. Area 2, well, again, we've got to then, we're going between two curves, so we've got to take the time and identify, well, what's the top curve, what's the bottom curve. So it's between 2 and 4, and this time that order is reversed. So what we're going to have is we're going to have minus x squared plus 4x minus 4, because it's the top curve, minus the bottom curve, which just happens to be x squared minus 8x plus 12 dx. And that's going to simplify to minus x squared, 0, 4x plus 8x, so we're going to have 12x, minus 4 minus 12 becomes minus 16. And again, I'm going to tell you now that when you go through and you evaluate that, what you're going to get is you're going to get 2 2/3 units squared. So combining those, then the total area is going to be 2 2/3 plus 13 1/3, which is going to equal to 16 units squared. So remembering with this question here, taking our time to find out where they crossed over, separate those two areas, ask ourselves what is on top, what is on the bottom. Alright, so with question 3 here, it says sketch the curve, or sketch y equals e to the power of x minus e, and hence find the area between the curve, the y-axis, and the x-axis. So let's jump in and have a crack at this one straight away. And before I start, I'm just going to give myself a reference graph. So y equals e to the power of x. Alright, remember that it crosses through our y-axis at 1. It has a horizontal asymptote at y equals 0, and it curves along like that. So we're going to have a very similar scenario that's going on here, but when we look at it, this graph that we've got here, sketch the curve y equals ex minus e. This e that's at the end here, pay very particular attention to it, that it doesn't have an x to it. It does not have the variable associated with it. So it is just a constant. Right? It's just a constant term here. Remembering that from graphs, if we have that constant at the end there, that's describing a vertical shift up or down. Alright, so we know that this whole graph has been moved down e units. Alright, So let's evaluate that. All right, because this curve has been shifted down E units, our asymptote has gone from being at 0 to now down E units. So our horizontal asymptote is now down here at the value E. Alright. Our y-intercept was initially, if we look back over here, was initially at 1. It's now been moved down, that y-intercept has been moved down E units. And remember, E is approximately 2.7 to be really, really crude with our rounding. So 1 take away 2.7, that's going to leave me below the x-axis. So let's say 1 minus 2.7, it's going to be 1.7-ish territory somewhere, so no. And that value there is 1 minus E. And then where is it going to cross my y-intercept? Sorry, not my y-intercept. Where is it going to cross the x-axis? Well, it's going to cross the x-axis when 0 is equal to e to the x minus e. So when, in other words, when does e to the x equal e? When x has a power of 1. So it's going to cross through my x-intercept at 1. So that curve, it's going to look, let's not do that. It's going to look something like this, and we've been asked to find this area here bound between the curve and both axes. Okay, hopefully that's okay. I haven't lost you anywhere there yet. So now that we know our curve, we know the shape, we just now need to do the area, and it's going to be between 0 and 1, which has worked out to be quite nice numbers, funny enough, of our function, which was e to the x minus e dx. And remember that we said that this e, because it doesn't have a variable associated with it already, that e was just a constant number. So when we integrate this, we know that e is its own derivative, so it's its own integral. Having a look at e to the power of x, the derivative of x is 1, which is out the front of e already, so we don't have to force a change on this. So it is just e to the x minus e times x. Okay, it's not e to the power of x, it's e times x, because e was just a constant. Alright, and we're going to evaluate that between 0 and 1, which is equal to e to the power of 1 minus e times 1 minus e to the power of 0 minus 0, e times 0, which is going to equal e to the power of 1 is e minus e, we're going to be left with 0, minus, when I look, e to the power of 0 is 1, 1 minus e times 0 is 0, so 1 minus 0 is 1, so it equals to negative 1, and then I go, uh-oh, got a negative area. Let's go back up. Remember, having a think about this, our area was below the x-axis. So without having to stuff around and changing all my signs, remember that our little trick we can do is just, well, it's the absolute value. It's the absolute value, it's the absolute value, it's the absolute value is an absolute value, so the area is 1 unit squared. Saves us having to change a lot of values there. We've been asked to show that in the interval, for example 4 here, between 0 and 2 pi, the curves of y equals sine x and y equals cos x intersect when x equals pi on 4 and when x equals 5 pi on 4. So we've been asked to show. So remember, with show questions, treat me or whoever's marking your work like they have no idea, like they completely got nothing when it comes to this question, yet they can read mathematical notation. The way we're going to do show questions is, identify what we can do. Well, here I've got this word intersect. So when two graphs intersect, that means they have the same solution. So I just need to know, when does y equals sine of x and y equals cos of x equal each other? So from my question, because I've got intersect, I want to know, when does sine of x equal cosine of x? That's what I'm looking to show from my question. And I need to show that this answer is going to end up being pi on 4 and 5 pi on 4. Now, just thinking intuitively, we know from our 45 set square that sine and cosine are equal to each other at 45 degrees, and 45 degrees is pi on 4. But how do we show this? Well, what do I know about sine and cosine? Sine minus sine, I could take cosine across to the other side, and I'll be left with sine minus cosine equals 0. So I'm asking, when do the exact two same values equal 0? Doesn't get me much anywhere. But I know something about sine and cosine. I can write them with tan. So if I divide both sides by cos, we know that then sine of x over cos of x is just tan of x. And cos of x divided by cos of x equals 1. So what we've been asked to do here is solve tan of x equals 1 across the interval between 0 and 2 pi. So x is going to equal to pi on 4, because it's 45 degrees. Right? We can do that. That's fine. And the other thing that we know to do, because we've got that x is positive, so it's a first quad and a third quad solution, because tan's positive in the third quadrant. Remember, the third quadrant is pi plus theta. So what we have here is pi plus pi on 4, which is just 4 pi on 4, plus pi on 4, which is 5 pi on 4. And that's exactly what we're asked to show here. Therefore, they intersect at those 2 points. So we know that sine of pi on 4 and cosine of pi on 4, well, they are just equal to 1 on root 2, which is root 2 on 2, because I don't like surds in my denominator, and then sine of 5 pi on 4 and cos of 5 pi on 4, they're just negative root 2 on 2 for the same reason. Alright. Cool. So part B says sketch the curves in this interval and find the area contained between them. Alright, so we've got our axes set up. We know that sine it starts at 0, goes up to 1, so do a nice smooth sine curve under pressure of the video. It's not too bad, and I know that that's going to be pi, I know that that's going to be pi on 2, and I know that is going to be 3 pi on 2, and over here is 2 pi. Cosine, remember it starts at 1, it's 0 at pi on 2, minus 1 at pi, so I need to come down here, reach -1 here, come up through here, and finish back at 1. So that's cos of y equals cos of x. This one is y equals sine of x, and we've been asked to find the area between them. Alright, we've been asked to find that, and what we know is that this value here is going to be pi on 4. We know that this value here is going to be 5 pi on 4. Right, we can see that, alright, from our curve. So we've done the sketching our curve part. Alright, moving on now and finding the area. Well, it's the area between two curves, so we're going to ask ourselves, where do they cross over? We've got that. We've got these intersection points here. Remember that that's 5 pi on 4 and minus root 2 on 2. And that point there was pi on 4, and it is root 2 over 2. Right, those are our points of intersection. And between those 2 points, we ask ourselves, is one curve always above another curve? And here we can see sine is always above cosine. So because sine is always above cosine, it's sine minus cosine is how we're going to evaluate the area. So the area is going to be equal between, we're going, the lower boundary is pi on 4, the upper boundary is 5 pi on 4, of sine of x minus cosine of x dx. Alright, if that's what we're evaluating our area between, remembering that the integral of sine is minus cosine, and the integral of cosine is just sine. So what we have here is we have, what did I say? We said we had minus cos of x minus sine of x evaluated between 5 pi over 4 and pi on 4, which that is going to equal, in our first bracket, minus cos of 5 pi over 4 minus sine of 5 pi over 4 minus cos of pi over 4 minus sine of pi over 4. Alright, and now let's be really careful with our negative signs here. We know that 5 pi on 4, it was minus root 2, so we have minus negative root 2 on 2 minus negative root 2 on 2 minus, and again, really careful with our minuses, minus root 2 on 2 minus root 2 over 2. So going through here, in the first bracket, these negatives and these negatives are going to make them positives. So root 2 on 2 plus root 2 on 2 becomes 2 root 2. So our first bracket, 2 root 2 on 2, sorry, so it's just going to become root 2 minus Over here, this one minus this one, we're going to get minus root 2. So our final answer is 2 root 2 units squared. Alright, hopefully that was okay. Be really careful with our negative signs, using brackets to make sure that we've got our, when we're substituting in, we don't make a mistake with our negatives, and just be really cautious, try not to rush this. Alright, your turn. Here are some questions from across a couple of different exercises. They'll cover off exponentials, hyperbolas, and trig graphs as well. Good luck with that, guys.